Assalamualaikum and hi, my name is Muhammad Zuhairi bin Zulkifli. So today I would like to present my final project. The title is The Effect of Hydrothermal Reaction Time on TiO2 Thin Film for H nanorod TiO2 Cu2O heterostructure thin film.
Okay, basically there are many types of material that used to fabricate thin film solar cell. But in this study, we choose TiO2 because of high photocatalytic activity, abundant material, low cost and non-toxicity. Then a new layer of metal oxide was suggested to combine with TiO2 to broaden its solar spectrum absorption. So we choose U2O because of low cost, non-toxicity, abundant material and the bandgap is similar. In this study, the effect of hydrothermal reaction time on TiO2 thin film still unknown. To optimize TiO2 nanorod thin film before conducting hydrothermal etching treatment and Cu2O deposition on TiO2 nanorod. Okay, this study aims to investigate the effect of hydrothermal reaction time on TiO2 nanorod thin film for H nanorod TiO2 Cu2O heterostructure thin film to characterize the structural, morphological, topological, optical properties and electrical properties. The problem of TiO2 is limited absorption of visible light. Because of the bandgap, TiO2 limit the solar spectrum. So we choose U2O as an absorbing layer because it TiO2 collect more photon by broadening its solar cell spectrum. And then CO2 fabrication of CO2 is not uniform because TiO2 has high resistivity and low surface area. So we implement etching treatment for properties enhancement. The objective of this study is to fabricate and investigate the effect of hydrothermal reaction time on N-type TiO2 nanorod on FTO, and then to fabricate P-type Cu2O on H TiO2 FTO nanorod using electrodeposition method, and lastly to characterize the structural, morphological, topological, optical and electrical properties of nanorod TiO2 and H nanorod TiO2 Cu2O heterostructure thin film. Okay, for the methodology, phase 1 substrate preparation and cleaning process, and then TiO2 nanorod preparation using hydrothermal method at 150 Celsius with reaction time vary at 7, 8, 9 and 10 hours. And then we do the characterization to select the optimum reaction time, and then the sample we undergo for hydrothermal etching treatment at 150 Celsius for 5 hours, and lastly Cu2O deposition on H TiO2 FTO nanorod using electrodeposition method at 60 Celsius for 1 hour. Okay, for phase 1, the FTO substrate will be cleaned using acetone, ethanol and DI water, and the solution is put into digital ultrasonic cleaner for 5 minutes stepwise. Next, TiO2 solution is mixing 60 ml of DI water and 60 ml of hydrochloric acid, and followed by titanium butoxide drop by drop 3 ml. Then put the FTO substrate into the Teflon with conductive side facing downward and pour with TiO2 solution. And then put Teflon into autoclave and make sure the autoclave is sealed carefully. And then put the autoclave in the oven and set the temperature at 150 Celsius and the reaction time is varied to 7, 8, 9 and 10 hours. After complete, take out the substrate and let it dry in ambient air. Okay, after complete, this is the TiO2 nanorod after hydrothermal method. For phase 2, the hydrothermal etching treatment, the solution is mixing DI water and HCl with concentration at 0.03 molar. The process is same with hydrothermal method, but the substrate is facing upward and the temperature is set at 150 Celsius for 5 hours. The CO2 solution is mixing DI water, lactic acid and cuprous acetate, and then add KOH until the pH value is 12. For electrodeposition method, we use 3 system electrode, platinum as counter electrode, substrate as working electrode, and argento chloride as reference electrode. Then the beaker is half immersed in water bath and put the electrode in Cu2O solution. Then put the thermometer into Cu2O solution to measure the temperature until 60 Celsius. Make sure the probe is connected to the electrode and use software Coreware to start the electrodeposition method. Make sure the connection is correct. The first result is the effect of hydrothermal reaction time on nanorod TiO2. Okay, first, structural properties. According to the standard JCPDS file, the 101 diffraction peak has the highest intensity. When the plane 110 was present at 27 degree at RT8, suggesting more TiO2 grow, the pattern suggests that the increasing reaction time enhanced the crystallinity of the film form. The TiO2 peak characteristics of sample RT8 are smaller, sharper, and have maximum intensity at 101 plane orientation, indicating better crystallinity. However, the existence of thin oxides peak at RT8 show that Increasing hydrothermal action time beyond 10 hours might damage the film synthesis. For morphological properties, we can see that the diameter and the thickness is increased. This table summarizes that the diameter and thickness increase with the increasing of reaction time. For topological properties, the roughness is decreasing, indicating that the longer reaction time can reduce nanorod TiO2 roughness. AFM also indicate a compact surface on the substrate. These findings are consistent with FE-SEM. As a result, it may be stated that hydrothermal grown TiO2 nanorod are encouraged to lower grain size, reducing the roughness of the film. For optical properties, the bandgap number confirms the crystallite size result, as a smaller crystallite size should have higher bandgap due to shorter reaction time. Meanwhile, as reaction time increase, the bigger crystallite size should have narrower bandgap, as a greater crystallite size should result in a narrow bandgap as the reaction time increase. For electrical properties, the resistivity of TiO2 nanorod structure is strongly influenced by thickness of the thin film. When reaction time of the hydrothermal process increase, the thickness of TiO2 nanorod increase, generating a storm barrier to electron while lowering sample conductivity. In summary, the RT8 sample revealed the most striking characteristic. This is because for RT10, the existence of thin oxide indicating that extending experiment beyond 10 hours could harm the film synthesis. When compared to RT7, the plane 110 was present at 27 degree and RT8 indicating higher TiO2 growth. The pattern show extending the reaction time increased crystallinity of the film. In comparison to RT9, the RT8 has low resistivity and low sheet resistance due to the sample thickness. Next, the effect of hydrothermal treatment on NTiO2 thin film. For structural properties, when the sample was etched with 0.03 molar HCl, 6 rutile peaks were seen at 2 theta. The etched TiO2 peak was smaller, sharper and more intense at 101 plane orientation, indicating brighter crystallinity. Even after etching treatment, the properties of TiO2 nanorod at orientation plane did not change. This demonstrates that the etching process has no effect on rutile structure independent on the peak intensity. For morphological properties, the FE-SEM image indicates the transition of nanorod into nanowire structure with deeper depth and the same shape of the side wall after sample etched with 0.03 HCl, and the thickness also is reduced to 2.64 micrometer. For topological properties, the obtained result indicate that the RMS roughness increased following the etch treatment. For optical properties, when the etching treatment applied, the bandgap value increased. This is due to the nanorod structure transitioning from nanorod to loose nanowire. The outcome is related to the sample thickness. For electrical properties, we can see that the resistivity and sheet resistance decrease due to the film thickness decrease. The last part is etched nanorod TiO2 heterojunction thin film. For structural properties, the largest peak in SRD pattern produced was 55.54 degree, which corresponds to 111 Cu2O plane orientation, whereas the highest peak in the etched TiO2 nanorod was 36.10 degree, which corresponds to 110 TiO2 plane orientation. The peak TiO2, both NTiO2 and P2O were exceptionally sharper, narrow, indicating great crystallinity. This demonstrates that the crystallinity improves as Cu2O ion diffusion becomes stronger, resulting in increasing Cu2O mass. For morphological properties, the illustration shows that the successfully deposition P-type Cu2O layer on N-type TiO2 nanorod. The pyramid form suggests that the existence of Cu2O on the surface of N-TiO2 layer. Between the pyramid shape Cu2O structure, there was no gap and holes. Also, the thickness of the sample is not significantly reduced in the cross-sectional. For topological properties, the RMS roughness of the sample is 122.74 nanometer. The obtained result show that the RMS roughness of the sample after electrodeposition process is attributable to the suitable temperature for Cu2O development owing to the fluctuation of the pyramid structure as proven by FE-SEM. For optical properties, the bandgap energy reduced when the electrodeposition process is used. As demonstrated in figure, the bandgap energy of the sample lower than the etched sample. The bandgap narrow as particle size increase, and the absorption edge shift to the higher energy as particle size increase. In conclusion, for the sample with titanium butoxide volume of 3 ml as optimal sample, the investigation was further to study the effect of hydrothermal action time. The hydrothermal action time is adjusted to 7, 8, 9 and 10 hours, and the condition remain consistent. By comparing the result, the RT8 show the dominant characteristic, and then it is possible to deduce that crystallinity of the TiO2 increase after etching treatment, with maximum peak intensity at 101 plane orientation be narrow, sharper and higher intensity. And then the sample after exchange treatment had the best and greatest RMS roughness. Is followed by the drop in resistivity and sheet resistance, which reduced. And this finding established that assuming the hydrothermal machine treatment on TiO2 nanorod film produced great behavioral qualities to improve thin film attributions. Apart from that, Cu2O thin layer is effectively formed onto HTiO2 nanorod substrate using electrodeposition method. The structural features of fabricated H nanorod TiO2 heterojunction thin film were studied, and it was discovered that the plane 111 preferred plane orientation dominate all samples. The Cu2O placed onto HTiO2 nanorod exhibit optimal structural characteristics as evident by the maximum 111 diffraction peak intensity from the collected SRD pattern, indicating high crystallinity. For morphological features, all samples display three-sided pyramid structure as resembled to the Cu2O thin film developed on the surface, with no void between grains, indicating a high degree of crystallinity. The bandgap show the minimum energy that is required to excite an electron up to a state in conduction band. That's all from me. Thank you.